Dear students, we are in Unit 4 of Differential Equation Person. In this lecture, we are going to discuss method of variation of parameters for solving linear differential equation. Before going into the details of this method, let us recall some of the methods that we have already come across in this unit so far. Namely, linear differential equation with variable coefficient, homogeneous linear differential equation, removal of the first derivative or reduction to normal form, transformation of equation by changing the independent variable, and exact differential equation. So in this lecture we are going to discuss the method of variation of parameters for solving linear differential equation of this type, or symbolically you can write dy by dx as y1. This is first order linear differential equation where p and q are functions of x or constants. So before going into the details of this method, let us also recall briefly what exactly this method is and what is the advantage of this method. Variation of parameters, also known as variation of constant, is a general method to solve inhomogeneous linear ordinary differential equation. So what does it mean? So I'm repeating, it is a general method to solve inhomogeneous linear differential equation. So what is inhomogeneous? So first you should know what is homogeneous. Differential equation is said to be homogeneous if the entire differential equation is equal to zero function. Say this will be homogeneous if q is equal to 0. So if it is not homogeneous, then it will be called inhomogeneous. Okay, that means you can say differential equation is said to be inhomogeneous if entire differential equation is equal to a non-zero function where q is not equal to 0. Then it will be called inhomogeneous. So as a side note, you should know that this method can also be applied to solve the partial order differential equation and homogeneous differential equation also. But this portion we are not going to discuss in this lecture. One of the most the biggest advantage of this method is that it is very general method, and this can solve large class of differential equation which cannot be solved by many of the previous methods. So this is the main advantage. Now let us see a working rule for finding the solution of first order linear differential equation using this method. In the first step, you just put the given differential equation into standard form. This is the standard form of the first order linear differential equation. In the second step, you just put q equal to 0, you will get this equation. Now in this step, our goal is to find the solution of this differential equation. Now this right hand side term becomes 0, so you can apply any of the methods to solve this equation. For example, you can use integrating factor. In this particular problem, you can use integrating factor because this is just a linear differential equation of first order, so you can use this integrating factor. Also, let the general solution of this equation 3.2, be given by y equal to au, where a is an arbitrary constant. So this is a hypothesis we consider in this step. In the third step, the general solution of the given differential equation 3.1, is given by this formula. So this formula unfortunately contains an integrand. So this can be taken as a disadvantage of this method, because we cannot give a guarantee that each and every term we get will be integrable. So it is in a way a disadvantage of this method. Okay. So what is ux? Ux is a function of x, or it can be simply written as u. Okay. Now let us discuss a simple problem based on this method. So this is a first order linear differential equation. It is to be solved by method of variation of parameters. So this can be, if the method was not mentioned, we can use any method that we have discussed to solve this. But here the method is mentioned, so we have to use this method. Just follow the working rule in the first step. Arrange this into standard form. This is in standard form now because the coefficient of this derivative is 1. This is done by just dividing the whole equation by x plus 4. Comparing this equation with the general standard form, you get q equal to 3 by x plus 4, or q equal to this much. Now you just recall step 2. When you put q equal to 0, you get this equation 3.3 reduces to this form, okay. Or after rearrangement and separating the variable, you get this expression. So it is needed because we want to integrate this expression. So it is now integrable. You can easily integrate. So integration of this will be log y. Integration of this term will be 3 log x plus 4. Just using the property of log, you get log x plus 4 raised to the power 3. So this right hand side is nothing but it is a log a, means it is a constant of integration. We are taking log because all the terms are in log. So it is just for convenience we have taken log. So this log a is nothing but c, constant of integration. So again by applying the property of log, we get this expression log y into x plus 4 whole raised to the power 3 and this term. Now cancelling this log both side, we get this expression, or y equal to this, okay. So just recall the step 2. In step 2 we make a hypothesis, that is, let the general solution of the equation number 2 be y equal to au. That means we make a hypothesis that the general solution of this equation is y equal to au. That means this differential equation. The general solution of this differential equation is assumed to be y equal to au. But the actual general solution we are getting is this. So these two equations are equivalent. So you can compare these two equations. This is a, this is a. This is u, this will be u. So u, this is u. Hence we choose u equal to x plus 4 all raised to the power minus 3. Now you just recall step 3, the last step. Then the required solution is given by y equal to this formula. Now in this formula you just put the value of u and q. All the values are given. So this is u, this is q and u. So after simplification, this term will give you x plus 4 all raised to the power 2. Okay. Now this is integrable. You can easily integrate it. Just for convenience, you can make a substitution. You can take x plus 4 equal to t. X plus 4 equal to t. This will give you dx equal to dt. So you put this, you replace this term by t. That means integration of t square. Integration of t square will be t cube divided by 3. T cube divided by 3. And again put back the value of t. That is x plus 4. So this is the final expression. Therefore the solution is given by y equal to, the solution of this equation is given by y equal to this. So after cancellation this will give you 1. Okay. So in the next video we will be discussing the differential equation, second order differential equation using this method.